Good morning, everyone. Sorry for being late. I was having some issues with the YouTube server today. Okay, so I had to actually I'm having to communicate through the backup server here. So please confirm if you can hear me properly. All right. All right. So today we're going to talk about certain Laplace transform properties. We have been talking about different properties of Laplace transform, and today we're going to actually talk about a few of them that are especially important regarding the application that we are looking for. Okay, and before we even start the discussion, uh, let's mention the properties that we are going to talk about today. We are going to talk about the property that is known as the initial value theorem. Let's say we are going to start with the final value theorem, maybe. Then we are going to talk about the initial value theorem. And finally, we're going to talk about the convolution property. All right. So these are the three properties that we're going to talk about in today's class. So since I am already late, I'm just going to wait for one more minute so that more of you can join. Then we're going to actually start the discussion. All right. So let's start with the final value theorem. Okay. So what is the final value theorem? The final value theorem actually can give you the final value of a certain inverse Laplace transform without actually requiring you to calculate the inverse Laplace transform. Okay. So what do I mean by that? For example, let me just give you an example here, just to show you what I mean. Okay. Let's say we have a Laplace transform of something. Of course, our approach, the way we are going to solve things, or um, where we are going to apply this kind of things, in those scenarios, what we usually do, we usually apply Laplace transform and then convert a differential equation to an algebraic equation, and then try to solve that algebraic equation. So eventually, what we get the Laplace transform of the output that we are calculating. So from that, we have to apply an inverse Laplace transform, right, in order to calculate the output in the time domain. But sometimes we don't need to know the output, but sometimes we just need to know what is the final value of the output. So what we need to know is that when the system has reached a steady state, what is the output of the system? That is something sometimes we need to know. So the thing is, if a system can reach a steady state, and of course a system can reach a steady state under a certain condition, it has to satisfy a certain condition. So under those type of conditions where the system reaches a steady state, we can actually figure out a way of calculating the steady state value of the output without actually calculating the total inverse Laplace transform. Okay, so that is exactly what we are going to learn in this one. Okay, so let's talk about the final value theorem. Just hold on for a second. All right, so let's start with the first one. Again, during the discussion, if you have any query, just feel free to ask me. All right, all set. All right, so not a problem then. All right, as usual, if you have any query, just ask me. All right, so let's start with the final value theorem first. And I'm going to show you a few problems with this, so that you can actually solve a few problems as we proceed here. Okay. Now, before we even actually talk about this, we are trying to calculate this thing. We are trying to calculate the value of something. Say if I have a function, something like x, we want to calculate the value of the function when time has become really large. So x is a function of time. So when time has become really large, we want to calculate the value of the function. Okay. But without actually ever calculating the inverse Laplace transform. Okay. So the thing is, I am given xs, which is the inverse Laplace transform of this. Okay, and it could be anything. Okay, so if I am given xs, which is the Laplace transform of xt, without actually calculating xt, without actually calculating the inverse Laplace transform and figuring out what signal it was originally, without actually doing that, I want to calculate this. So what is the final value of the signal xt? So if that is my goal, then we need to use the final value theorem. And alongside that, we are going to mention that important fact that not everywhere you can apply final value theorem. Okay, final value theorem has a certain condition that needs to be satisfied in order for it to be applicable, and that is something we are going to actually see. Okay, so I don't know what it is. I mean, I don't know how we can actually even do that. So to figure out a way, let's look at the different Laplace transforms of different things. For example, say we know that the Laplace transform, so let's see the different thing. Okay, so we know that the Laplace transform of a derivative of a signal, say of course xt is there. What is the Laplace transform of the derivative of this signal? So of course we know that the Laplace transform of the derivative of this signal is s minus x0. Now of course x0 is the initial value of the signal, and sometimes we consider zero initial conditions, but we are here writing the exact full formula. Okay, all right. So now we have to assume one important thing right away. Okay, right away we have to assume one important thing is that this signal xt that we are dealing with is a causal signal. So xt is causal. So that is an assumption that we are putting there right away. Okay, xt is causal, which means that is xt will be 0 for all t less than 0. Okay, so as long as t is less than 0, xt is going to be 0. So that's an assumption we are putting right away. Okay, so now what is the definition of the Laplace transform here? What is the definition of the Laplace transform? Of course, since xt is a causal signal, its derivative is also a causal signal, obviously. Okay, and as such, the definition of the Laplace transform would be like this. We have this, and then of course x dot t, then we have e to the power minus st dt, and then of course in the right hand side I have s xs minus x0. Not a problem, I hope, right? So now let's see what we want to find out. We want to find out when time reaches infinity here. When time reaches infinity here, I want to calculate the value of xt without actually calculating xt. Okay, I want to calculate this particular limit. So I want to calculate x infinity when time reaches infinity. So when the system apparently has reached a steady state, I want to calculate its value. Okay, but without actually calculating the inverse Laplace transform. So that is the objective in this particular scenario. So I believe you understand what I'm trying to say here. All right. So now at this point, so try to understand that this is an identity. Okay, this is an identity because this kind of relationship will hold for every possible signal. Okay, this is an identity. So this s, I can treat this s as a variable in an identity. So again, what is an identity? An identity holds for every possible value. So it could be any signal as long as it has a derivative and it has a Laplace transform. Okay, this relationship will hold. Okay, so this is an identity. Now of course, since this is an identity, we can put whatever value we want for this variable s. Okay, so that is exactly what we are going to do next. So we are saying that let's put this limit, and this thing will be evident shortly why we are doing this kind of things. So let's put a limit s tending to 0 on this, and let's write this integral once again, the derivative of this, then with e to the power minus st and dt, and that's going to be equal to limit. We have to do the same thing on the right hand side, s tending to 0, and then we have s xs minus x0. Okay, I believe it's understandable once again. So we just have taken a limit to the in the right hand side, right? Now, of course, if s is tending to 0, you see this is entirely irrespective of s. So this is devoid of s, and this does not have any dependency on s. So this limit will not affect this signal in any way, shape, or form, right? So this limit will only affect this thing. This limit will only affect this thing, right? So since that's a function of s only. So if I now calculate the limit, you see this will not be affected, but this limit will actually affect this part only, nothing else. Okay. And of course, what is the limit of e to the power minus st when s tending to 0? Of course, that's going to be 1, right? So because it is becoming e to the power 0, something like that. So under that condition, we can say this is like x dot t dt, because that is becoming 0 under this particular limit. Okay. And on the right hand side, we have limit s tending to 0, s xs minus x0. See, x0 is a constant. Okay, that's the initial value of x. Okay, that's the initial value of x. That's a constant. So of course, the limit does not do anything on a constant, right? So that is again, once again, devoid of the limit. Now we can look at the left hand side and actually do the integration. Now, what is the integration of the derivative of x? It is x, right? So it is going to be xt. And what are the upper and the lower limits? Of course, the upper limit is infinity, the lower limit is 0. And here on the right hand side, what do I have? I have s xs, sorry, a limit s tending to 0. I have s xs minus x0. All right. Now, with that being said, if I put the upper limit here, what am I going to get? I'm going to get something like x infinity. Okay. That is exactly what I sought to figure out. And minus, I have x0, right? So that's putting the upper limit and the lower limit. So what is x infinity denoting here? X infinity is actually denoting this. When time is very large, what is the value of xt, the original signal? Exactly. And on the right hand side, we have limit s tending to 0. I have s xs minus x0. And these two can be cancelled out because you can see they are the same thing. So what we have now figured out is that x infinity can be actually calculated without calculating the inverse Laplace transform, because this is equal to this limit. I shall show you an example that will be more evident in this. Okay, so that is going to be like that. So here we can now say that from this, if I just know the Laplace transform of this without actually calculating the inverse Laplace transform, I can actually calculate what is the value of this function xt, original signal, when t is very large. What I have to do, I have to multiply this with s and calculate this limit. Calculate the limit s tending to 0. So that will actually give you this. And of course, it has certain conditions. Okay, let me put the conditions right away. Okay, the condition is that, of course, we are writing an infinity limit here. Okay, we are writing an infinity limit here. And right there are the conditions. This must exist. This must exist. Okay. So this limit must exist. So it should not be infinity. It should not be undefined. And a sufficient condition for the existence of this limit is the stability of the system. Okay. So the condition under which the final value theorem is applicable is a condition that ensures that x infinity actually exists. So the limit we sought to find out, like this, actually exists. Okay. Only under that condition, this final value theorem is applicable. And the sufficient condition for that, okay, for the limit to exist, hold on, make a few more pages. Okay. And the sufficient condition for that existence is the stability of the system. Okay. So if the system is stable, then x infinity is guaranteed to exist. So that's again sufficient condition. I'm going to explain what I mean by that. Okay, the system xs is stable. Just hold on. Let me. Let's just write xs is stable. If xs is stable, And what do I mean by this table or whatever, I'm going to explain later on. Just keep in mind, this is the condition under which this final value theorem is applicable. Okay. So again, you might find in exams and in many competitive exams especially, that they will ask you to apply final value theorem, but they will give you a condition where this xs is not stable. Okay. So you cannot really apply the final value theorem under those kind of conditions. Okay. But let us see a condition under an example. Yeah. One of you saying, is it about the Bibo stability of the system? You are absolutely correct. But we are going to express Bibo stability in a slightly finer way in our course in control system. Yeah, this is bounded input, bounded output stability. So this signal has to be bounded, right? The idea is that this signal has to be bounded, and this signal must reach a suitable fixed final value, essentially. It should not even oscillate. Okay. So I'm going to explain what I mean by these terms here shortly. So don't worry about that. Okay. So let's see a few examples. Okay. Rather one example here in particular. Okay, here I am going to assume that the final value theorem is applicable, because I haven't yet shown you how to actually figure out a way to determine whether or not the final value theorem is applicable or not. Okay, but let us say that xs, we calculated xs. Okay, we calculated xs, and xs turned out to be something like, I don't know, 3s square plus 2s plus 9 divided by say s cube plus 6s square plus 11s plus 6, something like that. So this has to be coming from something that is stable. Okay, this should be a stable form. Okay, I'm going to explain what again. So this is again pertaining to Bibo stability. So we are going to explain this properly. Don't worry about that. Okay, just assume that this is stable. Okay, I've just given you a stable form here. Okay, so it won't be unstable and it won't cause you any harm here. Okay, it is not a problematic thing. So what I now want you to find is the value of xt. So if I just ask you to find the value of xt, you have to take an inverse Laplace transform on this. And let me assure you, taking an inverse Laplace transform on this is not very difficult, but not easy either. Okay, it won't be very difficult, but not easy either. Okay, so that way you might want to skip that part. So if somebody asks you to calculate xt, or if you need to calculate xt, then you have to you don't have any other way than to actually do the inverse Laplace transform on this. Okay, it would be very difficult, or rather a moderately difficult problem. This is a moderately difficult problem. Okay, to calculate the inverse Laplace transform of this, you have to factorize the denominator and do a partial fraction expansion, and you would see that exponentials, sum of exponentials, is the answer in this one. But nonetheless, I want to calculate not xt, but I want to calculate the initial value of xt. But before I even do that, let me verify this situation with actually solving this particular problem. Okay, with actually solving this particular problem. Now, in order to solve this particular problem, we need to actually factorize this. Maybe I just want to calculate xt. Okay, so in order to do that, I need to factorize the denominator. Now, of course, I have just given you the problem, so I exactly know what kind of factorization it is going to take. Okay, but this might not be as easy as this one. Okay, this might not be as easy as this one. So the denominator gets factorized as s plus 1 times s plus 2 times s plus 3. So this system has 3 poles. Okay, this system has 3 poles, as you can see. So this has 3 poles. So there are 3 values of s for which the system here xs is going to get an infinite value. Okay, and the numerator, forget the numerator, whatever that is, I don't care right now. Okay, but this has 2 zeros, because we see that it's a second order polynomial in the numerator, which indicates that I would have 2 solutions of it, right? If I write equal to 0, I would have 2 solutions, and those solutions will give me values for which, if I put them there, I'm going to get 0 in the numerator. So that way this entire thing is going to be 0. So those are called the zeros of a certain transfer function or a certain function here, like that. Okay, so if I put s equal to -1, I get an infinity, so that's a pole. If I put s equal to -2, I get an infinity, that's another pole. If I put s equal to -3, that's also another pole. So it has 3 poles and 2 zeros, right? So what I'm trying to do right now, I'm trying to actually do the inverse Laplace transform so that the results we obtain is verifiable. Okay, because we are going to apply initial value theorem on this and also the final value theorem on this. So this is an example which we are going to use for both of them. So I need to actually be able to verify what we derived. Okay. So of course, how do you do partial fraction? It's a very simple thing. Since the order of the numerator is less than the order of the denominator, we can just use the partial fraction expansion like this. So this is like this, and also everything in the denominator are first order expressions. So like that. I believe you already know these things, right? So that's the partial fraction expansion. Now, of course, there is a popular method that you don't know. It's called the Heaviside cover-up method. I'm not going to do that right now here. So I'm going to just talk about the standard method that you already know, in which you actually solve this kind of problems. So what you do essentially for this kind of partial fraction expansion is s plus 1 times s plus 2 times s plus 3 and a times s plus 2 times s plus 3 plus b times s plus 1 times s plus 3 times c times plus 3 times s plus 1 plus s plus 2. Okay, so the idea is that this kind of fraction can be written as this. Okay, so where a, b and c are constants because the order of the numerator is less than the order of the denominator and the denominator are all first order polynomials. Okay, so essentially like that. So this term, so this thing that I have here would be identical. So this term that we have here would be identical to the actual numerator. So actual numerator was this. So that term would be identical. And from this, once again, this is an identity. This is not an equation. Okay, keep in mind. We are saying that this term will be identical to this. So let's put an, instead of putting an equal to, let's put an identity symbol. Okay. So this term is going to be identical to this. And from that, since it's an identity, we know for every possible value of s, this is true. Okay. So what is the difference between an equation and identity? An equation is true for certain values of the variable. An identity is true for every value of the variable in the domain, of course. Okay. So every possible value of the variable, it's true. So for every possible value of s, this is true. And by that understanding, we can actually use certain values of s to figure out the values of the constants. For example, this identity is true for example, s equal to -1. Okay, because this is true for this identity, it has to be true for every possible value of s. All right. So if I put s equal to -1, then this identity must also hold true. Okay. So, but that will serve us a certain purpose because if I put s equal to -2, you see -1, you see this factor will vanish. Also, this factor will vanish because I have an s plus 1 factor in this. So that will become 0. So this factor will become 0. This factor will become 0. Only this factor will remain. And when I put s equal to -1, so this factor becomes a times 1 times 2. And in the right hand side, I have 3 minus 2 plus 9. And from this kind of formulation, we can actually figure out the value of a. And that way, we are going to figure out all the values of the corresponding constants here. All right. So this is going to be, a is going to be, so let me just make sure that I am writing everything correctly. 3 minus 2. Yeah. So please follow along the calculation properly. And if I make any mistake, make sure to tell me. Okay. So that's going to be 10 by 2. That's going to be 5. So we just figured out the value of a. Okay. A is 5. And that's exactly how we people have been doing this. Okay. So let's put a is equal to, say, for example, let's say this is, say, -2. Let's put a is equal to -2. Because again, this is an identity and this identity will hold true for any value of s here. Okay. So under this scenario, if I put s equal to 2, this will vanish. This term will also vanish. Only this term will remain. And as such, this will become b times -1 times 1. Okay. And that's going to be equal to, see here I have -2 here. So that's going to be -12 sorry, not minus 12, 12, and then minus 4 plus 9. Okay, 12 minus 4 plus 9. So that's going to be 17. Okay, right? That's going to be 8, 17. So B is going to be minus 17. So if I make any calculational mistakes, please let me know, because I might make a calculational mistake. Okay, and similarly, now I want these two terms to vanish, so I would put s equal to minus 3. Once again, because that expression that we wrote is an identity, so it should be valid for any value of s, and that's why we are picking and choosing certain values of s. All right, yes, you people are correct here then. Okay, so if I put s equal to minus 3, this term will vanish, only this term will remain. Okay, so there we have c times a minus 2 times minus 1. Okay, and on the right hand side I have 27, okay, minus 6 plus 9. Okay, one of you have already gotten the answer. Okay, 27 minus 6 plus 9, so that's gonna be 30. 30 divided by, so that's gonna be 30, right? 27 minus 6, 27 minus 6 plus 9, so that's gonna be c, 2c is equal to 21 plus 9, 30. So B is going to be 15. Okay, C is going to be 15. So one of you have got C is equal to 12. I don't know how you got that. I think C is going to be equal to 15 plus 15. Okay, C is going to be plus 15. Right, so these are the three values that I have for this. So the point being, from this we can actually replace these values. So we just figured out that this expression will be equal to like this, where A has this value, B has this value, and C has this value. So we can say the thing for which we wanted to figure out the inverse Laplace transform, XS, which was this. Let me just copy this. Which was this, and which we then said was going to be something like this, can be expressed somewhat like this. Okay, so we can say, now we know the value of A, B, and C. We can just put them here. So this is going to be something like 5 minus 17, 15. All right, so that's how we actually do the inverse Laplace transform. So applying an inverse Laplace transform on this to calculate xt would be just applying an inverse Laplace transform on that thing. So the inverse Laplace transform on that thing. Now, of course, we know that the Laplace transform of e to the power at ut is 1 by s minus a, and from that understanding, we can say that the Laplace transform of this first thing is 5 times e to the power minus t ut. Okay. All right. Similarly, the next one is minus 17 e to the power minus 2t ut, because of this formula again, once again. So a here is minus 2, okay, and plus 15 e to the power minus 3t ut. Of course, ut is only making the signal causal, okay, and that's obvious because we started with a causal understanding here. So we are actually going to use causal signals only, right? So everything that we have here are causal signals, and of course the corresponding systems are also causal. That's obvious, right? So we can actually factor out this ut out of all this. Okay, so we're going to have 5 e to the power minus t, then minus 17 e to the power minus 2t, then plus 15 e to the power minus 3t, all of them times ut. Now, why did I calculate this ut? Just to verify the next thing that we are going to do. Okay, the next thing that we are going to do. So keep in mind that this is our xt. So this is the inverse Laplace transform of whatever we had there. Okay. All right. So that, with that being said, now try to apply the final value theorem. Okay, let's say we want to calculate what is x infinity. What is x infinity? That is essentially the limit when t tending to tending to infinity, xt. I want to calculate that. What if I want to calculate that from this, directly from this, because we have actually calculated the inverse Laplace transform. So let's put the limit then. Okay, let us put the limit. Okay, so if I put the limit here and calculate this, okay, let's see what we get. So that's going to be limit t tending to infinity on this thing. Okay, let's put it there. Okay, please tell me what that is. What is it going to be? You see that this is going to be, so when t tending to infinity, this is going to be 0. Then this is also going to be 0. This is also going to be 0. So what is the final value of this thing? So 0, 0, 0 and times 1, then of course that's going to be 0. So we just figured out that the final value of this thing, the final value of this xt is 0. Okay, the final value of this xt is 0. We just figured that out, right? Of course, from the inverse Laplace transform. But what if we don't want to do the inverse Laplace transform? So we can actually calculate this from the original thing without actually calculating the inverse Laplace transform, because we know that x infinity can be calculated in another way using the final value theorem. What is the final value theorem? That says I need to calculate this limit s tending to 0, s times this limit. Now this is coming from the final value theorem. Okay, this is coming from the final value theorem. Now, of course, since this is coming from the final value theorem, I do not need to calculate the inverse Laplace transform because I have xs here. So you can see this can be calculated by calculating the direct limit here. Okay, x infinity means calculating the xt at t tending to infinity. So calculating the direct limit will actually give you the result. Or you can use the final value theorem to calculate it the other way around. So we are calculating this limit. Limit is tending to 0, s times xs. Now what is xs? Xs was this. Okay, that is exactly what we want. All right, so that is exactly what we are calculating here. Okay, so let's multiply the numerator and the denominator. So numerator with s, because I have an s here. So we are calculating limit s tending to 0, and then on the numerator I have 3s cube plus 2 s square plus 9s, and here I have s cube plus 6s square plus 11s plus 6. It is not an indeterminate form. This limit will be very easy to calculate because if I calculate the limit here, you can see this is still going to be a ratio, very simple ratio. So in the denominator, if I put the limit, this is going to be 0, 0, plus 0, plus 0, plus 6. So essentially in the denominator, I would have 6. And in the numerator, if I put the limit, I would have 0, 0, 0. So the numerator actually boils down to 0 as the limit is placed here. So this is not an indeterminate form. Okay, this is nothing, something by 0. It is not something by 0. It is not 0 by 0. It is not infinity by infinity. So it is a very well defined determinate form. Right. So it can be determined very easily, right? So this is 0 by 6. So of course the limit is 0. So you can see we actually did not do any hard job of calculating the inverse Laplace transform. Okay, because if our objective is only to find out the final value of the response, okay, final value of xt, like that, we can actually use the final value theorem like that. Okay, all right. So that is, I guess, understandable, right? Do you want me to do another example here? All right, so we're going to do a complete example once again after we discuss all of that. Okay. So this is your final value theorem. So without actually calculating, So one of you are asking, how would you know that we have to calculate the final, use the final value theorem? Yes. So you would know that you want to use the final value theorem when you don't want to actually do the inverse Laplace transform. Okay. See, when we applied the final value theorem, we calculated the final value of xt. We calculated the final value of xt, okay, without actually calculating the xt. So using final value theorem without actually calculating xt, you can calculate the final value of xt. That's the point here. You did not calculate xt here. You did not require xt. Okay, you just had the Laplace transform of xt. You had xs. From that, you can calculate the final value of xt. So when you don't want to do the inverse Laplace transform, or you don't have the inverse Laplace transform at hand, then you can actually apply the final value theorem to calculate the final value of the response. Sometimes we need this kind of things to know certain things about the system. Okay, later on it will be more evident. Okay, so if you have any query, make sure to ask right now. Please make sure to ask. Okay, not a problem, right? So let's now talk about the initial value theorem. This is also one of the most important theorems that we require in control system engineering. Okay, that was the final value theorem. Let's talk about the initial value theorem. We would approach the problem the very similar way, in a very similar way. Once again, our objective is now to calculate this x0. We want to calculate x0. Okay, what is the initial value of this without actually calculating the inverse Laplace transform? And look back, here we wanted to calculate x infinity, right? We wanted to calculate x infinity without actually calculating xt. Okay, similarly here we want to calculate x0, so which is like writing xt when limit t tending to 0. Now we have to say 0 plus, because again when it is 0 minus, it is 0 because we are assuming causal signals. But try to understand that we're just adding 0 plus here. Okay, just to indicate the fact that again when t was less than 0, xt is 0, because again we are assuming causal signals. Okay, got it? So that is something we have to assume. So this is nothing but limit t tending to 0. Okay, there is no confusion with this, but the only thing is that this is slightly positive. Okay, so we are not approaching the limit from the negative side. Okay, when we say limit t tending to 0, we are actually approaching the limit from the left hand side as well as the right hand side. And when the limits are equal, okay, then we say there exists a limit at this point. Okay, something like that. Here we are not approaching the limit from the left hand side, because we know that the limit from the left hand side is 0 already, because this signal is causal. Okay, so as long as t is negative, this is going to be 0. Okay, so we are approaching the limit from the right hand side. So this is the right hand limit, just keep that in mind. Okay, so this is often denoted as something like x0 plus. That indicates that the system has just started. Okay, so if I just write x0, that might indicate that okay, the system might not have yet started or something like that. So x0 here, x0 plus indicates that the system just has started. Okay, one of you are once again asking a question. What is the question? Here we only have to find the total value, 0 or infinity. No, it's not about 0 or infinity. It could be some other numbers as well. Okay, but here the final value theorem and the initial value theorem allows you to calculate the final value or the initial value of the signal xt without actually calculating the signal. Okay, so if you have the Laplace transform of the signal, by looking at the Laplace transform of the signal, you can actually tell what is the initial value of the signal and what is the final value of the signal without calculating the inverse Laplace transform. That's the objective here. Okay, now this can be calculated by using this limit directly on the signal. You can actually calculate this limit. Okay, but if you don't have xt, then what can you do? So you have just xs, the Laplace transform of the signal. You don't have the inverse Laplace transform, so you don't have xt. then how can you calculate the initial value? Okay, so initial value theorem is very easy to understand. As a matter of fact, we are going to write this very line that we wrote here, or rather these two lines that we wrote here. Okay, for the proving the final value theorem, we are going to write those back in here as well. So let's just copy and paste them. Okay, not a problem, I hope. Okay, so again we are taking the Laplace transform of the derivative of this thing, and here we have this. Okay, once again not a problem. Now here we are just saying that this limit is going to be 0 plus. Once again we are ignoring the limit on the left hand side, on the what should I say, on the limit on the left. So left hand limit, we are ignoring that. Okay, and as such we are just putting up 0 plus here, because we know that if x is slightly less than 0, then this is also going to be 0. So technically speaking, this should be the correct limit formulation there. Okay, so no, it is also once again not a very difficult thing to see. Okay, any confusion there? I guess if you have any, please let me know. This is just a small mathematical detail. You can actually ignore. You can just happily write x0. No one will argue because you are an engineer, right? So now let's put a limit, just like before. Now instead of putting that s equal to 0, let's put s tending to infinity, because we have an identity here. This is not an equation, truly speaking. This is an identity. Okay, so this is, even though we are putting equal to sign, this is an identity. So this should be valid for any value of s, even infinity. So let's put that limit. And as you might have guessed, I mean, this is, since this is a constant, okay, a fixed value, the limit actually does not affect this term at all. So this is going to be sxs minus x0. So this is devoid of any limiting quantity there like that. So this limit is not applicable on this, okay, because this is a constant. Okay, now here of course, as before, this limit on s is not going to affect this term, because this term is completely devoid of s. So the only function that has anything to do with s will be affected by this, nothing else. And of course, if I put s tending to infinity on this, you'll see what happens here. If I put s tending to infinity, let me just write it explicitly so that no one gets confused with this. So I get x dot t, and this limit here, limit s tending to infinity e to the power minus st, and then we have dt, and on the right hand side we have. Now look at this. Look at this. When I put s tending to infinity, what happens? This is becoming 0, right? Because t is positive. T is positive. Okay. So since t is positive and s tending to infinity, so this is becoming 0. So this thing is 0. So when I'm multiplying something with 0 and integrating this, we get a 0. So the left hand side is a 0, because this is going to become 0. This thing is going to become 0. Okay. And on the right hand side, we have this once again, right? And just like that, we can say x0 plus is this limit s tending to infinity sxs. Okay, just like that, you can actually calculate that. So this is your final value theorem, sorry, initial value theorem. So we are calculating limit s tending to infinity sxs. Okay, let's once again try to see the application of this using that example. Okay, using this particular example. Okay, we saw an example. Let's see the same example once again. Okay, let's see the same example. So we want to calculate x0 essentially. Okay, we want to calculate x0. So x0 is nothing but 0 plus whatever, nothing but limit t tending to 0 on xt. Okay, so 0 plus. Okay, so slightly higher than that, xt. Now of course I have xt because we calculated the inverse Laplace transform, so that's xt. Okay, and of course we have to put the limit there. Now of course if I calculate the limit here, So if I put 0 here, what happens? So this becomes 5, essentially this becomes 1, 1, 1. So this becomes 5 minus 17 plus 15 and times 1 here, because ut is 1 as long as t is positive, and that's why we have this sort of a limit. Okay, so that's the initial value of this. So what is that? That's going to be 20 minus 17, so that's going to be 3. So that's the initial value of the output. Okay, so rather the signal, initial value of the signal. So if we have the inverse Laplace transform, we can directly put the limit. But if we don't have the inverse Laplace transform, okay, so just like before, if we don't have the inverse Laplace transform, so here what we did, we have the inverse Laplace transform and we can actually calculate this. But if we don't have the inverse Laplace transform, then we can actually apply the initial value theorem. Okay, and say we are going to say that this limit also gives you exactly the same value. Try to see the difference. If I just want to calculate this directly, I have to know the inverse Laplace transform. But if I don't know that, or if I haven't calculated that, we can actually use the initial value theorem to actually calculate that without the need of the inverse Laplace transform. So let's see. So we had the original thing. Okay, xs. What was xs? That was xs, right? Without actually doing any calculation on that, any modification or any inverse Laplace transform shenanigans on that, we can actually directly calculate this limit. Now, what is the limit here? Sorry, I have to multiply this with s. Just hold on for a second. Okay, can anybody calculate the limit? I'll be back in a second. So try to calculate this limit here. Yes, one of you have already gotten the correct answer. Now, how do you calculate limits to infinity? That's a very easy thing. You divide with the highest power of that thing. So we are calculating limit with respect to s here. Okay. Now, when s is tending to infinity, how do you do that? How do you calculate this? You just divide the numerator and the polynomial, numerator and the denominator with the highest power of that s. So again, many of you have already received the answer. So limit s tending to infinity. So now here we are dividing the numerator and the denominator with s cube. Okay. So if I do that, I would have 3 plus 2 by s plus 9 by s square. And here I have 1 plus 6 by s plus 11 by s square plus 6 by s cube. Now we can happily put the limit, because here you see that if I put s tending to infinity, which is a very large number, this is becoming 0. So this term will become 0. this term will become 0 because this is once again something by a very large quantity. Similarly, this term will become 0, this term will become 0, this term will become 0. So all of them will become 0, and as such we are going to be left with 3 by 1. So that's just 3. So that's the initial value, and that is exactly what we figured out by directly applying the limit on the inverse Laplace transform. Okay, but for this we need to have the inverse Laplace transform, right? What if we don't have the inverse Laplace transform? We can then apply the initial value theorem to calculate the initial value of x, just like that. So these are the two use case scenarios of the initial value theorem and the final value theorems. Just to mention, this initial value theorem is more liberal kind of, so this is sort of applicable to any transfer function or any Laplace function here, like that. So this is sort of like a transfer function. So for any transfer function, this is kind of applicable. Okay, the initial value theorem is more or less applicable to any transfer function. No such complicated condition. Okay, but for the final value theorem, okay, this condition must be satisfied that the system, that xt is should be a Bebo stable thing. Okay, that xs should be a Bebo stable system. Okay, so that is the condition for the final value theorem. So final value theorem is not always directly applicable. Okay, is not always directly applicable. To just give you an example where final value theorem might not be applicable or is not applicable. Okay, just to show you that, let me just show you an example like that. Let's say an example, initial value theorem is almost always applicable, almost always. Okay, and you won't encounter a situation where the initial value theorem is not applicable. Okay, at least in your course. Okay, where the systems are seesaw, rational, linear, time invariant, you won't encounter a system that is where the initial value theorem is not applicable. But you can very easily encounter a system where the final value theorem is not applicable. Let me just give you an example. An example where the final value theorem is not applicable. Okay, and the example is a very simple example, like xs is 1 by s minus 1. Yeah, you might see, oh, that's a very silly example, simple example. Okay, let's apply the final value theorem. I am asking you to calculate x infinity. Now what is x infinity? X infinity is of course limit t tending to infinity on x t. But let's apply the final value theorem. If I apply the final value theorem, then it's going to be limit s tending to 0 s xs, right? This is from the final value theorem, right? So let's calculate that value. So limit s tending to 0, so I have s times 1 by s minus 1. Okay, so we are putting that value s equal to s tending to 0. So it's again a non-trivial limit, a very trivial limit. So in the numerator I have, just hold on again. All right, so I have once again 0 divided by minus 1, so that's 0, right? So you might be tempted to say that the final value of this signal is 0. Okay, so this x infinity, so which is when t tends to infinity, the final value is 0. You might be tempted to say that. Okay, but this is wrong. Let me show you why. Because we have xs, and we can actually take the inverse Laplace transform very easily, because this is a very simple example. Okay, here what is xt? We took the inverse Laplace transform. That's going to be e to the power t ut, right? So this is 1 by s minus a, where a is 1. Okay, so this is going to be e to the power t ut. So what I wanted to figure out was x infinity. What is the value of xt when t is a very large number? So limit t tending to infinity xt, right? So this is the actual way, not using the inverse Laplace transform. Sorry, not using the final value theorem. So if I calculate that, so we are going to calculate limit t tending to infinity on e to the power t, and ut is of course 1 on there. So what is this limit? So this is going to be e to the power infinity. So e to the power infinity is a really, really large number. So this limit actually goes to infinity. This limit actually goes to infinity, and you can see this in the picture as well. So if I draw a picture of this, the response or whatever the value here will start like this, and from there it will jump here at t equal to 0. It is going to be 1. It will jump there, and from there it will rise and rise and rise, so something like that. It is going to go to infinity. Okay, so this is exactly what it is. So this is e to the power t and ut. So this is of course t, and this is xt. So of course the limit when t tending to infinity here is going to be infinity, because this is going to rise exponentially. But the final value theorem gave you a different answer, in fact a wrong answer. Okay, so the final value theorem gave you a different answer. In fact, a wrong answer was given by the final value theorem. So you might understand, so from this you should, that final takeaway from this is that the final value theorem is not always applicable directly. Okay, so the point being, this is due to an unstable system. Okay, this corresponds to an unstable system. Okay, this corresponds to an unstable behavior. Okay, and you can see that from this picture here, this is never reaching a steady state. Okay, since this will never reach a steady state, this is always going to rise and rise and rise and rise, increase and increase. This is never going to go to a steady state. And since this is never going to go to a steady state, this is not corresponding to a stable scenario. A stable system, when you apply a certain bounded input, always reaches a steady state in the output. So this does not converge. Yes. So this does, no. It's not about s equal to 1. It's not about that. It's not about s equal to 1. It's not about that. It's about xt. Okay, it's about xt. Okay, it's about xt. And you see that the final value theorem is not applicable here. The final value theorem is not applicable here. Okay, so this is an example where the final value theorem is not applicable. Let me show you a very similar example where the final value theorem is applicable. Okay, and there for that, all I could just take this is applicable. I can just take this example and make it a plus. Okay, and now let's apply the final value theorem. Let's apply the whole thing here. Okay, now you will see that this is now applicable here in this particular example. This will be now applicable, and why is that so? We are going to learn shortly. So let me just make this green. Okay. All right, so we have a plus sign here, and we have a plus 1 here. The answer is nonetheless 0. Not a problem there. Okay, the answer is nonetheless 0. So the final value theorem is telling you that the final value of the response here in this one is going to be 0. Final value of the signal is 0 in this one. But let's check that. Let's check that. Okay, using the same analogy here that we checked it earlier. You can see that this is now a plus here, and this is going to be that way. This is going to be a minus TUT, and if we calculate the limit here, that limit is now going to be e to the power minus infinity. You see, that's a 0. So now the limit here directly is matching up with the result that we obtained from the final value theorem. Okay, and that is also visible if you draw the picture. If you draw the picture of xt, again we are drawing the picture of xt. Okay, drawing the picture of xt, not xs, keep in mind. So t and xt, if you draw the picture of xt, it will look somewhat like this. It will be 0 at this point, and here at t equal to 0 it is going to jump to 1, and then from that it is going to be an exponential decay. And this exponential decay will eventually turn it down to 0. Okay, so this is e to the power minus t ut. So that's how the final value theorem is applicable. This signal is bounded. The point being that signal has to be bounded for the applicability of the final value theorem. Okay, so let me just go back to the final value theorem discussion, and let's say this must exist, or in other terms, x infinity must reach a fixed steady state. So it must reach a final value in order for this theorem to be applicable. Okay, so this has got nothing to do with the poles or zeros. See, you can see One of you said that it does not converge at x equal to 1. Does not have that does not have anything to do with this, because similarly it does not converge at x equal to -1. Okay, it has got nothing to do with that. It has got everything to do with the convergence of the inverse Laplace transform. Okay, and how do we even now? Question is obviously, how do you ensure the convergence of the inverse Laplace transform without calculating the inverse Laplace transform? Because you are seeing that we are now in a situation where we do not know whether the inverse Laplace transform actually converges or not, whether xt actually converges or not. We do not really know unless we calculate the inverse Laplace transform. But if we calculate the inverse Laplace transform, our entire objective is defeated. Our purpose is defeated, because what is the utility of the initial value theorem or the final value theorem? Their utility is mainly to calculate the initial value of the inverse Laplace transform or the final value of the inverse Laplace transform without calculating the inverse Laplace transform. But for example, to apply the final value theorem, you need to know whether the inverse Laplace transform is a converging function, okay, whether it converges to a certain final value, right? But how can you even do that without calculating the inverse Laplace transform? Because you are trying to avoid the inverse Laplace transform, but in order to avoid that, you have to calculate the inverse Laplace transform. So we have a dilemma here, right? And that is exactly what we are going to solve in our class, where we discuss stability of systems in the next one, very next one. Okay. So in the very next one, we are going to actually discuss the stability of systems, and there we are going to understand that how we can actually assess the stability of a system without actually calculating the inverse Laplace transform, calculating the signal and looking at the signal to figure out whether it is bounded or not. Instead of doing that, we are going to actually figure out, we shall be able to figure out the stability of a system without calculating the inverse Laplace transform. Okay, so just to give you an idea, this is corresponding to an unstable situation, and this is corresponding to a stable situation. And once you learn how to distinguish between these by looking at a transfer function or looking at a system function like that, you will be able to tell whether the system is stable or not. Of course, stable in the sense of BIBO, okay, bounded input, bounded output, stable or not. Okay, you shall be able to figure that out without actually calculating the inverse Laplace transform. So that is one of the objectives there. So that is, I guess, understandable and hopefully cleared up the usage scenarios of this, right? So any confusion so far, please let me know if you have any confusion. I would just wait for a minute and then we're going to restart. All right, so let's now talk about the other theorem that we wanted to discuss today. That's the convolution property of Laplace transform. Again, we discussed a lot of properties earlier, and this is the final one that we're going to discuss for this class at least. And there are a few other properties that we are skipping over. Okay, of course, I would suggest you rather consult a book on that. Of course, we would consult Ogata's book on this. So that's the final theorem that we want to discuss here. Convolution property. We're not going to call it the theorem, but rather the property. Okay, so let's go back to our systems, discussion on systems. Okay. All right. Okay. So this is a system for which if I apply an impulse input, I get the impulse response. You understand that? And of course, this is an LTI system, so linear time invariant system. So the impulse response gives you all the knowledge that there is to know about the system, right? So this system is described through this impulse response. So GT is the impulse response of the system. Okay, GT is the impulse response. Okay, now then we know, again we derived this in our signals and systems classes, that if we now excite the system with any arbitrary input xt, then we can actually calculate the output of the system if I know the impulse response. Okay, so xt is any arbitrary input signal. And yt is the output due to xt input. So when we applied xt as the input, the output that we obtained is yt. Okay, so that is something we know. And then of course in our signals and systems classes we derived that the output can then be calculated. Of course this comes from the linearity and time invariance property. Okay, then output can be calculated by doing a convolution between the xt and gt, these two signals, right? So that is exactly what we can do. And again, convolution by default by itself is a commutative in nature. So if we can figure out a system for which xt is the impulse response and gt is the input signal, that will produce the same output. Okay, so if I have a system whose impulse response is gt and we excite the system with an input xt, output will be yt. In the reverse case, if we have a system whose impulse response is xt and we excite the system with an input signal gt, we are going to get the same output, because convolution operation is commutative in nature. And the operation that we denote, so between these two, is with a star. Okay, this star here is indicating that we are convolving gt and xt. So that is the convolution operation. This is the convolution. Right, so that's the convolution operation, and not a problem, I hope. Right, so again we already know how to actually calculate the convolution of two signals. We know it mathematically, that the convolution of two signals is denoted like this. So from negative infinity to positive infinity. Once again, while deriving the property, we are not going to assume what should I say, causality here. Okay, okay, so you have a question regarding the initial value theorem or the final value theorem. Okay, I am not going to answer your question right now, because when we discuss stability, it will be more evident on why we need these kind of things. Okay, so we talk about stability and then we are going to come back to answering your query. Okay, and regarding convolution, we are going to use convolution for a different objective completely. We are not using convolution to check whether a signal is bounded or not. Okay, all right. So of course we know that this is going to be g tau x t minus tau d tau. Of course we actually derived all of this in one of our earlier classes in signals and systems, of course. So that's the convolution. Okay, now let's apply Laplace transform on this whole thing. Okay, so let's apply Laplace transform on this whole thing, and it's not a very difficult task, but keep in mind the moment we apply Laplace transform, it will become a double integral, just like with the Fourier transform. This is going to become a double integral here. Okay, so let's apply a Laplace transform on both sides, and the moment we do that, we will have a Laplace transform here, and we are going to have a Laplace transform here. That's going to be g tau x t minus tau d tau. Okay, just hold on this bottom property. All right, so that's fine, right? Now, of course, in order to make sure that you do not confuse yourself with whatever I'm writing here, okay, I'm just going to use different inks to represent all this. Okay, of course, the Laplace transform of yt, the Laplace transform of the output, is now going to be denoted with ys. Now, of course, we have to do the calculate the Laplace transform, and this is the signal for which we are calculating the Laplace transform. Okay, so how do you calculate the Laplace transform? Using this integration from negative infinity to positive infinity. Okay, on whatever signal you have, and what is that signal? What is that whatever signal? And that is it, right? So this is that signal for which you are on which you are calculating the Laplace transform. So this is the signal on which you are calculating the Laplace transform. Okay, so just keep that in mind. And then we have to multiply this with e to the power minus st and integrate it with respect to t. That's how you calculate the Laplace transform. Just keep in mind that this thing is the signal itself. Okay, just hold a second. So of course, this integration is this yellow one is coming from this convolution. Okay, so to make sure that we can distinguish everything while we go along in this, we are going to use different inks to describe different things. Okay, so this integration is happening for the convolution, and this blue one is happening for the Laplace transform, for the calculation involving the Laplace transform. I don't think it's a difficult thing to understand. Any confusion so far? We're just applying the Laplace transform. Okay, we're just calculating the Laplace transform. Okay, right? Now, since you can see this integration with respect to tau, for this integration with respect to tau, this is a constant. Okay, just like we did it in Fourier transform. So this is a constant as far as this integration is concerned. So actually, while integrating this green one here, while doing this green integration here, this is a constant. If it was inside this, still it won't affect our calculation in any way, because this integration is happening with respect to tau. So this factor will be treated as a constant. So that is exactly what we are going to write next. And the next line, we are going to write this integration. Okay, then this integration. Then of course these things, g tau x t minus tau, and this can be brought inside because that won't affect the calculation. So let's use a yellow ink, and we have d tau and we have dt. Okay, this can be brought inside because that won't affect this, because this is once again not a function of tau, because this integration is happening with respect to tau. Okay, I have to take another page. All right, let me save this just one minute. Okay, all right, so not a problem, I hope. Now there is a certain trick in double integral that is called the change of variable. Okay, change of variable or change in the order of integration. Now there are certain conditions under which this change in the order of integration is applicable. But if we have a form like this, in general the change in order of the integration is applicable. Okay, I'm not going to teach you the mathematics of double integrals right now, but assume that the change in the order of integration is still applicable here, holds true here. Okay, so what we do, we are changing the order of integration here in the next line. Okay, so this would happen under certain conditions. This does not always happen. Okay, there are situations under which this won't happen, but in this particular scenario, this can happen. So what we are doing, we are changing the order of integration. So we are doing the green integration first, okay, with respect to tau, and then we are going to do the blue integration with respect to t. Okay, you see the order, right? So first we are integrating with respect to tau, and then we are integrating with respect to t. So we actually change the order, and of course whatever was there inside actually remains like that. Yeah, it won't be a problem, but we have just changed the order of integration. So we are going to say changing the order of the integration. And again, once again, let me repeat. I mean, this does not always happen. Okay, you cannot just always change the order of integration like that in a double integral. But under certain scenarios, certain cases, this can happen. Okay, under certain cases, this can happen. Okay, just keep that in mind. Under certain cases, this can happen. Okay, okay. Understood. Not a problem. Okay, so okay, just keep following along, and I hope it's going to be understandable. Okay, so once again, we are going to have a laboratory class tomorrow, and there we whatever discussions, whatever confusions you have, you can just bring that up. Okay. All right. So now look at this blue integration here. Okay, the inner one, the blue one. Here you see that integration is happening with respect to t. So whatever that does not have t can be treated as a constant. So this g tau is a pure function of tau. It's not a function of t. So that can be treated as a constant as far as this integration is, this blue one is concerned. So that can actually go outside this. So on the next line, this is what we are going to write. We're going to write this integration and this bring this gt outside, g tau outside, because the blue integration is with respect to t, and that won't affect the result finally. Okay. And then we are going to do the blue integration here. I'm going to do this minus infinity to infinity on this xt minus tau e to the power minus st, and of course we have dt. Okay, so since that is not a function of t, it can go outside this integration of with respect to t. Okay, so I don't think that's also a very difficult thing to understand. That's not a very difficult thing to understand either, right? So now this is just like the Laplace transform. So what is this? This blue one. What is this? This is the Laplace transform. So I told you, of course, not I told you, we derived this. We know that if the Laplace transform of xt is xs, then the Laplace transform of the time shifted signal is e to the power minus as times xs. We knew that, right? That's called the time shifting property, right? So this is here, you can see this, let me just write it once again. This is going to be minus infinity to infinity. That's going to be g tau, and here this blue one is nothing but the Laplace transform of xt minus tau, right? Isn't it? This blue integration is just nothing but the Laplace transform of xt minus tau, right? And of course, from that we know this is going to be e to the power minus a tau, okay, xs, okay, this is going to be minus e to the power minus a tau xs. So let's just write it once again. So this is going to be this integration. I would have g tau, and this is going to be e to the power minus s tau xs, okay, because of this property here, the time shift property, and we have t tau. Okay, not a problem there. So let's just bring this to the side and give this as a side note. Okay, all right, I believe so far it is not a difficult thing to understand. Now of course we are integrating with respect to tau, so this xs has got nothing to do with that tau thing. Okay, this xs has got nothing to do with this tau thing, so that can actually go outside this whole integration thing here. Okay, so we can now say that this is going to be going outside this whole integration thing. So this is going to be, so we have this integration like that, and it's going to be on g tau. Let's write e to the power minus s tau. We have d tau. Okay, and outside we are going to have xs, because that's going to go outside the integration, because the integration is not going to affect this. This is going to be treated as a constant for this integration here. Okay, I hope that's also understandable. Okay, now this is what? This is once again the Laplace transform, because this is the same thing as the Laplace transform with the name of the variable changed. Okay, if we just do a trivial substitution here and change the name, like instead of writing tau we write t, okay, you see that this is the very definition of Laplace transform, right? This is the very definition of Laplace transform. Since this is sort of like a definite integral with respect to t, limits won't affect whatever variables we have, so the variables names won't have effect here. So ultimately this is going to be a Laplace transform, right? This is the very definition of the Laplace transform. Okay, so we can just do a trivial substitution and replace tau with t in this integration, and we would get the definition of Laplace transform. So this is nothing but the Laplace transform of gt. Okay, and as such this is gs. Okay, and of course we had xs outside, so let's just write it. So we can see the Laplace transform of the convolution of this. So we actually started to figure out the Laplace transform of the convolution of these two signals, and we figured out that the Laplace transform of the convolution of these two signals is the product of the individual Laplace transform. So what we figured out was the Laplace transform of the convolution of these two signals. So Laplace transform of gt convolved with xt is equal to the product of the individual Laplace transform, gs times xs. Okay, the product of the individual Laplace transform. So this is your convolution property. Okay, now this is very usable and pretty nice, and of course we have seen this being used, okay, in our earlier classes, because now we can, instead of saying this and instead of calling this a property that has something to do with convolution and such, what if we take Laplace transform on this whole thing? What if we take Laplace transform on this whole thing and we say, okay, the system's impulse response, the Laplace transform of that is gs, whatever the input was, the Laplace transform of that is xs, and the Laplace transform of the output is ys. Then instead of calculating the output through this convolution operation between the impulse response signal and the input signal, we can calculate the Laplace transform of the output by multiplying the Laplace transform of the input, so the Laplace transform of the impulse response, with the Laplace transform of the input. So this immensely helps in our situation, because now we can do very complicated operations. So for example, if we have a cascade system here, okay, we have another system here. What if we have another system here? So then this goes into this ys goes into that, okay, and whatever is the Laplace transform of the impulse response, that is what it gets multiplied with, and you get the output. So this is now in the Laplace transform domain, this is just like acting as an amplifier. So this is the input signal amplified by this much, is like a number, it's like a number now, okay, it's amplified by this number and you get another number, another signal, right? Just like 5, 4, 6, whatever, amplification with gain certain, right? So this becomes like a gain in the Laplace transform domain. So when we apply the Laplace transform, this becomes a gain term. All right, so that is exactly what is happening, and that's why we have this kind of nice relationship. And of course we then have defined, we can now say gs is nothing but ys by xs, and that is the definition of the Laplace transform, that definition of the transfer function. Okay, and of course we defined transfer function pretty earlier in our class, so I'm not going to get to the same discussion once again, but that's it for today. All right, so we have just seen three most important properties that we regularly use in our control system classes and for understanding control systems: the initial value theorem, the final value theorem, and the convolution property. Okay, we have seen other properties as well earlier, but we're going to use all of them. So in the next class we are going to have a discussion on S. Okay, now we did not describe this S, or rather mention what this S is really, okay, and what is the physical significance of S. As far you have figured out that S is sort of like a complex frequency type of quantity, okay, frequency type quantity. But what is that? What is the physical meaning of S? We are going to describe that in our next class, and then on the next class we are going to derive a property of linear time invariant system that allows us to check whether the output will be bounded without actually calculating the output. Okay, so in other terms, we would figure out a way in which we shall be able to see whether the system is stable or not without actually calculating the output of the system. Of course, if we could calculate the output through inverse Laplace transform and could check whether the output was bounded or not, then we could actually reasonably say the system is stable or not. Okay, but we are not going to do that. Instead, we are going to figure out a way in which, without calculating the inverse Laplace transform, without calculating the output itself, by looking at the system, we shall be able to tell whether the system is stable or not. That is going to be the objective in the next one. Okay, so we're going to, next class we are going to learn how to understand S as a complex frequency quantity, and also how to analyze or assess the stability of a linear and time invariant system. So those are for the next one. Okay, so far if you have any query, feel free to ask at this moment. Otherwise, we are going to end the discussion at this point. So if you want me to show a few more examples, you can ask me. Okay, otherwise you can actually do that in our laboratory classes, right? Okay, that's a very good question, I hope. Okay, that's a very good question. Let me just okay, one of you asked, okay, how did this become Laplace transform? Okay, you might have this kind of questions. I assumed that. Okay, so before even actually do this, let me just tell you, let's say GT is a signal, right? GT is a signal, and what is the Laplace transform of GT? Say we say Laplace transform of GT is GS. Okay, so what is the definition of Laplace transform? This integration, right? GT e to the power minus ST dt. Notice very carefully that this is an integration with respect to t. So when you do the integration with respect to t, after that you replace the t with the limits. You replace the t with the limits. Okay, you replace the t with the limits. So if instead of being t, what if this was something else? What if this was tau? Would it affect the ultimate result? Because you are going to do the same integration, and in the end you are going to replace the limits. You are going to substitute t with the limits. Just like, for example, if I ask you to do this integration, okay, integration from this to pi by 2 on sine at, okay, dt. This integration, the result of this is going to be exactly equal to sine omega t dt. This is going to be exactly equal to, sorry, not omega t at, this is going to be exactly equal to sine a tau d tau. This is also going to be exactly equal to the same integration where I have sine a p dp. You understand what I'm saying? Because this is a definite integral, and in the end you are going to get something in terms of p, but you are going to substitute that p with the upper and the lower limit. That this variable is going to be substituted ultimately with the upper and the lower limit. So essentially you are going to calculate the limits on this. Similarly, since you are going to calculate the limits on this, it's the same thing, because ultimately you are going to calculate a function with respect to t and s. The result will be in terms of t and s, but we are going to calculate the limits with t. So t will be substituted with the upper and the lower limits. So t will not be there, just like tau won't be there. So this is still the Laplace transform of GT. Just like all these integrations would give you the same result. Okay, and just like that, okay, we see that's the thing. Okay, that's a very interesting question. The limits have been long there, has long been there before this. Okay, that's a very good question once again. The point being, I'm not substituting anything. I just told you to assume that sort of a substitution in your mind. I just told you to assume that sort of a substitution in your mind. I never asked you to substitute a t like that randomly. Okay, because this is exactly equivalent to this calculation. I just asked you to assume this equivalence in mind. You can define GS in any way you want. Okay, instead of calling this tau, you can call this p, whatever you want. You still get GS, right? These are just the same thing. Okay, I just wanted you to understand that, because you want to calculate the Laplace transform of GT. you can calculate in any way you want. So the name of the variable could be anything you want. Okay. So this is again, this tau is kind of a dummy variable because ultimately this is going to be replaced by the limits. Okay. So this is exactly equivalent to writing this, and this is the time domain to S domain. That's a very good thing here. You can assume that tau is also a time here. Isn't tau time here? Because see, we're writing t minus tau here, right? Okay, t minus tau. Isn't tau also some sort of a time? Okay, that's a very good question. Once again, Laplace transform converges from time domain to frequency domain. I'm going to explain what frequency domain means and what time domains really mean. But the thing is, what is tau? Isn't tau time? Because if tau is not time, then we cannot subtract it from time. We can only add two terms or subtract two terms if they have the same unit. Okay, so if t is time, then tau is also time, right? So this is nothing but transforming it from time domain to frequency domain, right? But again, it is tau is not time. Just to give you once again to explain what I mean to say here, tau is time, okay, and that's why we can actually subtract this here. Try to understand the causality here. Try to understand. I am saying, tau is time. Tau is denoting time in some way. Okay, that's why we can do this subtraction. It is not the other way around. Because we are doing this subtraction, tau is a time. That is not the thing. Okay. You cannot say because we are subtracting this, that's why tau is a time. Okay. Because we can subtract tau from t, tau is being considered as a time. It is not like that. Tau is a time quantity, and that's why we can subtract it from t. So it is just the other way around here. Okay. Tau is a time quantity, and that's why we can subtract it from t. And this will be very evident in our next class, where we describe S as a conjugate variable of time. Okay, in mathematics, there is something called conjugate variables. So time and frequency, they are going to be conjugate variables. T is going to be a conjugate variable of S. Okay, and you will later on see that this idea of conjugate variables is not just in control system engineering. There are many other different types of conjugate variables. Okay, and from that you can get a very nice insight about systems. Okay, about how these things really work. Okay, so that is going to be left for the next class, and any question you might have, feel free to ask at this point. Again, this is going to be a side note, I hope. Otherwise, let's say side note. All right. Any questions so far? I mean, of course, any question in the end. Right, so if you don't have any more questions, I'm going to see you tomorrow, right? And thank you very much for patiently attending the class. I'll see you tomorrow.